Welcome, everyone. Today I'm meeting with Dave Kammer, Greg McLaskey, and Elisa Tinti, and we'll be talking about their recent perspective on energy dissipation in earthquakes, why it is so challenging to monitor earthquake energy dissipation, what is earthquake energy dissipation, what's earthquake energy, and most importantly, how does this affect our understanding of earthquakes, and how can this hopefully impact in a positive way earthquake forecasting and monitoring in the future? So stay tuned. Right. Yeah. So if I understood this correctly from my email conversations with Dave, you organized a workshop focused on the topic of energy dissipation during earthquakes, or at least you had a workshop on earthquakes, and this was one of the topics. And as a result of this workshop, you were writing this perspective on energy dissipation. Before diving into the work you are presenting, can you maybe explain us a little bit more what we understand under earthquake energy and why it is such an important parameter to study?
So maybe just to clarify, none of us, or maybe I do it wrong on Elisa, but we didn't organize the workshop. We participated in. Our colleagues organized it, and which was a really nice event. And we had very good discussions, very intense discussions, and that's why we wanted to have something that lasts from the workshop. That's how we ended up working on that. Maybe it's important to first say what an earthquake is, so that we can clarify. So in earthquake, as we all probably know, is a crack propagating along a fault, and I'm an engineer, so please apologize for imprecisions here. But the mechanical understanding of this is that you have energy being loaded in the system of the tectonic plates as they are being loaded over the times, the years, and so on. This is energy stored like in an elastic spring, that you pull apart. It's just in the rock. And then at some point, the fault in some area is too weak to hold. It will start sliding, and the way it's nucleating is a big topic of research as well. But at some point, it becomes unstable, and you have this crack propagating through the fault, which is essentially releasing this energy that is being stored in the crack. And it's like releasing the spring that you pulled. And then this energy has to go somewhere, and so it's being split into different parts. One part is the radiated energy, the seismic waves that we all feel. That's what we perceive as an earthquake, or all of us when we experience that. But then there is energy that is being dissipated on the fault through friction that generates heat, through some weakening process. And there is energy that's being dissipated in the rock around. It's a bit vague, but maybe because we don't know all the details about it, by creating additional cracks, by damage accumulation, and so on. And so it is really this transformation of the stored energy into these three other types of energies that is directly related to how the earthquake behaves. And so that should show you already how important energies are for this process. Maybe my colleagues have some more detailed statements for that.
Yeah, I guess I'll add just a little bit that this energy dissipation is kind of just one part of an energy balance. And I think Dave mentioned this, but basically it controls, at least in theory, it controls how fast the earthquake rupture propagates. And that is in turn controlling how much shaking we feel. And it also controls whether or not the earthquake rupture stops or continues to propagate. And that would control the size of the earthquake, whether it is a small one or whether it continues to propagate and grows very large.
Only one thing that I can add for this whole very clear explanation is that when we record the energy in the station, we are able to see something that arrive at the stations, so also far from the fault. While the energy dissipation that is dissipated on the fault or around the fault is more difficult to be measured. So while we have a more clear understanding of the energy that reach the sensor, so that we call radiated energy, we have more difficult, constraining to compute the energy that is dissipated on the fault or close to the fault, in the volume around the fault.
Thanks. Yeah, I think that's already leading up to my next question, because that's one of the main motivations of your perspective, that it's actually so difficult to monitor energy dissipation, both in the field, but also in the lab. So can you explain a bit more why it is so difficult to monitor it, or what are the main challenges?
Okay, if I can continue, our direct observation of recorded waves can tell us something about radiated energy, so what we see at the sensor. And if we have a closer sensor, will be the better condition. So also for the actual and recent seismic network, we have a lot of data, but it's very difficult to find a network that has a lot of sensor very close to the fault. So the closer, the better, but it's very difficult for the moment. And the energy dissipated as radiated energy is only a portion. And so we try to understand which kind of the best measure we can have for this dissipation close to the fault. And also it's important because this energy dissipated close to the fault and on the fault has very different scale length and time length. So it's very different from the total duration of the event. So this is why it's so challenging, this kind of measure.
Yeah, I'll just add that even in the lab, we might have a little strain gauge that's only 5 millimeters from a fault. And what happens is the signature that would relate to this energy dissipation, it gets distorted as you get further and further away from the fault. And so you either need to be so close to the fault that it's not distorted, or you need to model that distortion with something. And then you don't know whether your model is correct. So the challenge, I think, is that we don't know. It's hard to know if you're close enough to get an undistorted picture, or if you're not close enough. Yeah.
I guess then diving into the actual core of your perspective, you're then, of course, proposing a number of incentives to address these challenges, both near field and far field, to better measure this energy. Can you walk us through what you propose to address these issues?
Well, maybe incentives is not exactly the right term, in the sense that we obviously are all motivated in trying to push the field forward, but we're trying to bring out what are the essential questions that we should be focusing on that would help us making a significant step forwards. And so that's where we are aiming for. What are the questions that are really challenging, that we need to answer? And what are the tools that we can use to answer these questions? One particularly important question we had in there is that, there is a framework that is relatively commonly used to describe earthquakes and also their equivalent in the lab, which is these fracture mechanics theories. And it has been shown that these theories work very well for the lab. And that is presumably because in the lab, the conditions are very well in line with the assumptions behind the theory. Now, the question is, are the conditions in the Earth also in line with the theory, or aren't they? I mean, we know they're less perfectly in line, but are they far away or not? And so then the question comes up, can we then still apply this theory to try to explain and analyze what is happening in the Earth while it's working in the lab? Is it working in the Earth? And we don't know. And so many of the questions we raise go around highlighting what aspect we would have to look at in order to determine whether the tool is capable of doing that in an accurate or good way, or what would have to be adapted to make it useful for the complex system as in the Earth.
Thanks for the clarification. So following up on this, now as we know the main questions that we need to ask, are there already any plans in place to address these questions, or what are the next research steps that need to be taken?
I think that we have to keep in mind that we have different framework and different point of view. So we have lab people, so people that study earthquake in the lab, people that study earthquake by using observations or record data, and people that are trying to understand what happens in the fault. So during this kind of rupture that propagate on the fault through theoretical model and so through the modeling. So all of these group of researchers have to be, how do you say, try to answer to these key questions. So try to understand how important are the different processes, when these processes can occur. So can be different for small or large events, can occur always or not, like melting or something that include heat or something. So heat production, I mean flash very, very fast, or other kind of chemical processes, or also the heterogeneities that we can have on the fault, because you know that when we start from theoretical one, we try to impose everything very simple, ideal, like mathematical one, while the fault are geological one, so are very heterogeneous with a lot of roughness, and the heterogeneity is also on the stress. And for example, the stress is one of the unknown parameters that is a challenge for us to understand, and can help us also to answer to our key question about the energy dissipation. And we have to remember that earthquakes are one of the greatest natural hazards, so it's very important to try to answer to these questions.
I think, a lot of our recommendations in the perspective are to do some more modeling, right? But I think that this perspective definitely helped focus, if you're making a model, you can explore almost anything. So this perspective said, hey, we should probably look, focus modeling on these questions, right? One of them was the role of the dissipation processes right near the rupture front or the rupture tip, as opposed to dissipation processes that happen, further away from the rupture tip, and under what circumstances can those dissipation processes further away from the rupture tip actually control the propagation of the earthquake, or whether or not it stops? For me, that was one of the big sort of takeaways.
I want only to add, if it's possible, that what Greg said is that is very important, because if this dissipation affect the rupture, this affect also the arrest of the event, so also the magnitude. So it's more important that we try to understand also the arrest, because we would like to, forecast in some way also how big can be an earthquake in this kind of condition. So everything is important for the nucleation, the propagation, and the arrest of a specific event.
Going beyond modeling, though, the thing I learned the most is we need to talk to each other. And it's very difficult, because there's lab people, there's modeling people, theory people, geology people that are looking at the structure and the fabric of the rocks. There's a lot of information, and I think the solution's going to come from integrating. Maybe I'm biased, but I think the solution is going to come from integrating the constraints from all of these different areas together. And that's one of the things that this perspective paper really did for me, is it helped me understand a little better Elisa's perspective and other people's perspectives, right?
I think you covered all my other questions I had about the implications because obviously studying this does have implications on earthquake observation, earthquake forecasting. So when looking this from a hazard perspective, so that's really great to hear. And then I think my other question was, because I realized you have, I think 13 people, you made collaborate 13 people for this perspective, all with a different background. And I guess there were both challenges, but also benefits in making so many people with such a diverse background collaborate, right?
Yeah, I think that is accurate to say. it was a challenging process to go through that. It required a lot of how should I say, willingness to try to understand someone else's perspective that is maybe against one's own arguments or one's own convictions, and so that took a long time. This is also why it took a really long time to write this thing. But it also had this benefits of causing really nice discussions and made some changes in how we look at things. And also, I think what it caused is that we maybe clarified a little bit the language, because some terms have been misused from some fields, because maybe there it's a little bit differently applied. And so we tried to unify that a little bit, and hopefully this will support also the process of communication between different people from different backgrounds in the future.
And Dave did a really good job. He was a good leader because he's very patient, It's hard to get so many people to agree on anything. And so, I mean, I'm putting his own words in here, but basically he said, focus on the things we agree on. And then when we disagree, formulate it into a question, right? Like, maybe this is something that we need to study further.
Okay, yeah. Thanks a lot. I think these were all the questions I had. So thanks for your time.
Sebastian, I have one other thing I could add,
Sure.
Right, you have I don't know about you, but I'm really impressed with the weather prediction these days, right? At least for me, 3 days, 5 days away, you can know when it's going to rain. And this is kind of the model that I think earthquake physics maybe should try and strive for is, how do they predict the weather 3 days in advance? They have a physics-based model. Basically, they understand the equations, and then they have a continuous stream of data helping to input the model and adapt the prediction in real time. We could do the same thing with earthquake science. The amount of data we have now is like 10 times more than it was 20 years ago. The seismic networks are advancing very much, but it's possible that we don't have the equations right. So that's sort of where we're trying to come in, is like, basically it's much more difficult for earthquakes because everything is happening deep underground. The observational challenges are great, but it's possible that the mechanics and the physics of earthquakes are not known well enough either, and that's perhaps another impediment to being able to predict earthquakes. And so this energy balance and energy dissipation, it's really at the heart of the physics and mechanics of earthquakes.
Do you think we will be there one day, being able to reliably and accurately forecast earthquakes?
Well, maybe Elisa has different opinions. Probably it's always going to be, like when it's going to rain, it's 50% chance or something, right? So it's going to be somehow stochastic. It's going to be statistical in some sense, but I think there's a good chance that it can be a lot better, maybe orders of magnitude better than it is today. I don't know. I think it does depend a lot on what we find, right? Because there is some inherent predictability or unpredictability depending on which physics is right. But I think we can do a lot better.
I can also only add that the prediction of an earthquake is still impossible. Nobody at the moment predicted any earthquake up to now, but all the studies is for sure focused on try to understand some precursor, something that is changing, something that evolving on the fault, on the volume around the fault. So everything that help us to better understand the earthquake mechanism, so also energy balance and so on, can help us to understand some precursor in some way. So everything that allow us to improve our knowledge and put some point, some fixed point on the physical processes, as Greg said, can help us to say something more. So, for example, now there are a lot of people that try to understand something from the AI, so from the artificial intelligence, but can be a magician and can give you an answer that maybe is not possible, not physical. So we have always keep in mind that there is a physical process that has to be followed in some way. So we have to try to improve as much as possible our knowledge. So I think that our key questions can help us and can help the community to go in this good direction.